Hello, welcome to Latency Exchange. On this channel, we discuss technical topics relating to low latency trading, concentrating on the exchange side concepts, technologies, and processes. I'm Dave Beattie, a solutions architect specializing in low latency exchanges. In this standalone video, I'll be looking at the widely deployed technical solutions supporting time services. Firstly, we will look at the technical requirements for a common time reference across an enterprise estate, and we will then move on to consider the solutions. When a project is set up to deploy a time services solution, one of the initial questions that get raised is how accurate do you want the time on the end host to be? The typical response is as accurate as you can get it. Fine. If you want all the servers to be nanosecond accurate, you'll need to find me a very large amount of money. Once the business pick themselves back up off the floor, they will ask, what do we need to do? Within the financial services world, this is governed by the MiFID II directive. But this is a very broad target, and it's not generally appropriate for the task. For an exchange that works at modern speeds, that is, it has a gateway-to-gateway latency of less than a millisecond, the maximum permitted divergence from UTC under MiFID II is 100 microseconds. At this stage, the operational teams usually add that they need much higher accuracy than 100 microseconds. They usually say that they need sub-nanosecond accuracy, but in the final analysis, they usually state they need accuracy of between 10 and 100 nanoseconds, with a resolution of 100 picoseconds. In some cases, they may stretch this resolution requirement to 10 picoseconds, but this is rarely beneficial, being so far below the accuracy requirement. In order to obtain the true time of a log entry on a server, it's imperative to know the server's offset from UTC at that time. For this to be known, an ongoing plot of UTC offset needs to be recorded, either on each server or on a central server dedicated to this function. In addition to this, if the recorded offset exceeds a specified threshold, some form of alerting will be needed. This not only triggers triage and remediation, but it also becomes a data source for discovery of periodic issues. Finally, the scope of the requirements will need to be determined. Such requirements are usually tiered. For example, the entire estate may need to have an offset from UTC of less than 10 milliseconds. The server estate may need that to be less than 1 millisecond. The exchange servers may need to squeeze that offset down to 10 microseconds. And the low latency servers may even need that to be down around 10 nanoseconds. This then allows a solution to be designed to meet the stated requirements at an appropriate cost. It should be noted that there are likely to be company-specific requirements to be added to the list. This might include costs, both CapEx and OpEx, availability or lead time, integration time, especially if any new software needs to be regression tested or certified for use. For the highest level of accuracy, new hardware may be needed in terms of specific network cards and switching infrastructure, and even an annual certification may be required. For each of these requirements, a method of measurement and validation should be determined. For example, when a maximum offset is determined, is this an absolute maximum, a 99th or 95th percentile, or a standard deviation? Who do these figures have to be presented to for approval, and in what format? For preference, an understanding of the criticality of a failure should be determined. That is to say, that if a device falls outside of the required threshold, what action is mandated? Should a failover be instigated? Just a remediation attempt? Or should it be left to the end of the business day? The stock solution for enterprise time services is NTP, network time protocol. This is able to produce offsets of 100 microseconds with care, but medium offsets of 1 to 10 milliseconds are more normal. There are two modes of operation for NTP, broadcast and unicast. There are currently very few installations using broadcast NTP in an enterprise scale manner due to its inefficiency, and unicast is fairly ubiquitous. The accuracy of NTP is loosely a function of the round trip time between the source and the consumer. However, as with all time services, path asymmetry can significantly impact the accuracy of the time algorithm. Packet loss and jitter in the path can also skew the results, but a good client can usually allow for this. However, it is debatable whether it is worth using a good client at cost with an NTP solution to help smooth out these path issues. Network quality of service settings should also be used to reduce packet loss and jitter. NTP authentication is usually mandated by the information security team. This is generally a good idea for NTP servers or nodes, but support for this can be unpredictable on client devices. It should be noted that some nodes only support authentication as a global option, meaning that it has to be either on or off for all connections. NTP architecture is based on strata, with 0 being most trusted and 15 being the least. In theory, a stratum 0 time source is pure UTC. This should be locked to UTC and unwavering. There are very few true stratum 0 sources. Connections to these sources are usually very tightly controlled because of the risk of overwhelming the source and affecting the accuracy of the time signal. Stratum 1 is usually used for high-level distribution nodes, either on the internet or on private networks. Access to these nodes is usually still by subscription, but less rigorously controlled. Stratum 2 is usually used for general distribution nodes, access to which is not generally controlled. It is also often used for enterprise edge or ingest nodes, where a company brings an NTP time source onto its network. The structure below this varies widely from company to company, but consistency within a company architecture is key to achieving the best possible median offset results on client devices. What is a node? A node can be any device that can process and serve NTP. In many cases, the best type of node is a bespoke appliance, but this is by no means necessary. The most common type of node is simply a Linux server, either physical or virtual. Windows servers are less prevalent. I've also used network nodes, switches or routers to support this function. The key factors here are that the node must have a reasonably good internal clock, which does not need to persist across reboots. It must also be able to handle the anticipated number of client connections without impacting other functions. Most NTP nodes can make use of up to 8 NTP sources, with a further 8 in reserve, but this gets difficult to administrate. The optimum number of sources is 4. With just one source, if it fails, there's a total loss of time signal, and the UTC offset will start to wander. With 2 sources, there is a backup for the primary, but if the 2 sources start to diverge, the node has no way to determine which one should be trusted. With 3 time sources, the nodes can use all 3 time signals and determine its own best view of UTC, allowing for a single divergent source. However, if one source disappears, we are left with the issues related to having only 2 sources. With 4 time sources, the accuracy of the solution is not improved, but the issues above are mitigated. In most cases, the node is able to use all 4 time signals to arrive at its best view of UTC. This means that each stratum should offer 4 sources to the one beneath. With each stratum, sets of 4 nodes should peer with each other to maintain a reasonably close common view of UTC. They should have 4 sources. These can be the same source for all of the nodes. They should be locked down so that no other time source can affect their view of UTC. The only exception to this would be where external sources are being ingested into a company or a network on dedicated links. In this case, the sources cannot share with multiple nodes. This is where an ingest stratum is helpful. Nodes in that stratum can have a single source each, and inter-node peering is used to mediate UTC from the respective sources. Client nodes can then access as many of their respective distribution nodes as they are able. In some cases, it may be preferable to use a virtual or anycast address on the distribution nodes to provide a resilient service to client nodes that can only support a single NTP server address. So what might a good NTP architecture look like? We would start with 4 ingest nodes. Each node would have a separate low stratum source. In this case, we have a subscription source over a dedicated link in London and New York, a subscription internet service in Chicago, and 4 free internet services in Madrid. The 4 nodes form a full mesh of peerings in order to maintain a reliable view of UTC. Each of the 4 offices then has a set of distribution nodes that peer within the locality and take NTP feeds from the 4 ingest nodes. A load balancer is set up to point to the 4 distribution nodes to provide resilience to clients that cannot accept 4 sources. DNS is set up for this as ntp.office.com, with NTP 1, 2, 3, and 4 pointing to the respective distribution nodes. It is preferred that clients are configured with the DNS names, but IP addresses can be used if DNS is not supported by the client. While NTP accuracy is assumed to be 1 to 10 milliseconds, it is generally accepted that a client device can maintain this accuracy in the absence of the NTP service for at least an hour. Beyond this, the system clock may skew away from UTC at a rate that is dependent upon the quality of the internal clock. If the client node were to reboot during this period, there should be no reliance upon the clock after the restart. There are some standard failure modes that we should consider. Failure of a source would cause one of the ingest nodes to lose its low stratum source. It would then draw its time from its peerings with the remaining ingest nodes. Divergence of a source would be arbitrated by the ingest nodes. Failure of an ingest node would cause the distribution nodes to have just 3 sources, and time would be arbitrated at this stratum in order to continue to provide full service to the other clients. Divergence should not happen at ingest or distribution tiers due to their peerings. If it does, it would indicate that the NTP application or service is at fault. Restarting this service should resolve the issues. Clients that use 4 distribution node sources should not be adversely affected by this. Single source clients, however, may find that their time skews away from UTC. The final failure mode to consider is a loss of the enterprise WAN. In this case, there are likely to be bigger concerns than NTP, but point-to-point VPNs could be used as an alternative. The NTP traffic profile is very light, so this is not a major concern, but it should be avoided if possible, because this can add round-trip latency or path asymmetry, which would affect the accuracy of the NTP calculations. When the achievable offset of NTP is not sufficient, most solutions move across to PTP, Precision Time Protocol. This protocol is able to achieve much better offsets due to its inherent assumptions of a fast, reliable, and uncongested network infrastructure. If these assumptions are not correct, PTP will not be able to provide the expected level of improvements to the UTC offsets, but is still likely to outperform NTP by quite some way. At the level of offset that is expected, the accuracy of PTP calculation is based on a number of factors. Most importantly, path latency asymmetry between the source and the client. This could be due to asymmetric traffic patterns and loads sharing the same links. Physically asymmetric paths, as can easily happen with link aggregation or overlay networks, or different forwarding methods within a node, as happens with the change of link speed. Round trip time. Although this is less important than asymmetry, this can still have a significant impact, because as this rises, so the absolute value of the asymmetry is likely to rise. Node processing capability. If a PTP node struggles to process the PTP updates sufficiently rapidly, it is likely to introduce variability into the resultant time feed, which will affect all downstream nodes. Advanced network interfaces. When a node has network interfaces that support advanced features like timestamping or kernel bypass, these can be used to mitigate processing limitations of the node and improve the overall accuracy of the PTP algorithm. Advanced client functionality. Significant improvements can be made to the UTC offsets by using advanced client functionality. Such functionality includes the ability to recognize and discard delayed packets, as might happen if a packet hits a temporary interface queue. Similarly, a packet that arrives too early is also an indication of a topology change or other unwanted behavior. Unlike NTP, a PTP solution can only have a single master clock at any one time. This means that if multiple clocks are needed for resilience, the first function that must occur is arbitration. The aim of this is to select the best master clock and present it to the remainder of the infrastructure. After this comes the distribution architecture. There are two general topologies available: boundary clock and end-to-end. Within a boundary clock topology, all switches in the path act as a client to their upstream device. They interpret the PTP signal and form their own view of UTC. They then become a master to their downstream nodes, either further switches or client devices. The main issue with this method is that switches often have limited processing power, and this is shared with all other processes. This introduces variability into the PTP algorithm. I've seen this produce 50 to 100 nanoseconds of variance at each node. Such switches rarely have advanced network interfaces or client capabilities to help to mitigate such variance. The benefits of a boundary clock topology are that it's easy to set up, it's widely supported, and it mitigates any path asymmetry issues because each link is point-to-point. For this reason, if the offsets resulting from a boundary clock topology are good enough to meet your requirements, this is usually the option selected. End-to-end topologies typically outperform boundary clocks in terms of optimum reduction of UTC offsets. However, they rely more heavily on a fast, reliable, and uncongested network that runs at a single speed or carrier rate. End-to-end solutions allow all of the clients to negotiate directly with the grandmaster. Intervening switches simply forward the traffic, either unicast, multicast, or both. This is done in hardware on the switches, so it's much less likely to impact the time feed. There are some solutions that allow switches to tag PTP packets with their forwarding latency. The aim of this is to enable the client to improve the accuracy of its PTP calculations. I've never had much success with this because it relies too heavily on inter-vendor cooperation. The PTP protocol falls into two parts: sync and delay. For boundary clock solutions, this has little impact. However, for end-to-end solutions, some care is needed. The sync message sends out the UTC time from the view of the grandmaster, and the delay message aims to calculate the forwarding latency from the grandmaster to the client. This delay calculation is unique to each client. Various parts of these message streams can be unicast or multicast. It makes logical sense for the sync to be multicast, and the delay, also known as follow-up, to be unicast. But some clients do not support this configuration, forcing all communications to be multicast. As can be expected, an end-to-end solution can lead to a large number of client devices interacting with the Grand Master. This means that the Grand Master must be scaled to handle this level of interaction. The accuracy of PTP can be significantly improved by using White Rabbit, a reference to the Lewis Carroll character. This uses capable interfaces to enable synchronous Ethernet or Sync-E, and hence locking together the clock frequencies of neighboring nodes. Ultimately, all clocks in the infrastructure will be synchronized, rather than free-running. This provides PTP with an unchanging architecture, allowing it to correct any offsets, leading to an almost universal agreement on UTC. This does rely on relevant support in any nodes in the path. It also relies on support for Sync-E across the infrastructure. Since Sync-E is a layer 1 feature, this means that even interface optics and repeaters must support it. This moves the network paradigm back towards point-to-point dark fiber links. As an alternative to White Rabbit, the older PPS technology can be used. This passes 1 pulse per second over dedicated cabling on dedicated interfaces from the clock source to the client nodes. This is then used to synchronize the internal clocks on the nodes, and PTP can be used to establish the exact time in the same way as it is for White Rabbit. The downside of this is the need for dedicated hardware on every node and dedicated cabling. Now a PTP example. A company has 2 data centers with 2 PTP nodes in each. Within each data center, the nodes synchronize using PTP and White Rabbit over a dedicated point-to-point path. Between data centers, synchronous Ethernet is not supported by the WAN provider, so basic PTP is used. Each node has 4 potential PTP sources. Firstly, its own GPS antenna. This is calibrated with the length of cable between the antenna and the node. The second source is via the GPS antenna on its peer device. The third source is from one of the PTP nodes in the opposite data center. The final source is a PTP service provided by the DC operator. The configuration of the priority of these sources is a matter of the technical policy of the company. Critically, there should be a specific decision regarding linking the time domains in the 2 data centers, or to simply log the respective offsets. Within each data center, a small dedicated PTP switch block is used. PTP end-to-end mode is used with hybrid transport wherever it is supported. Full multicast can be used where hybrid is not available, but this increases the volume of traffic seen by all nodes. If any clients do not support end-to-end mode, they must connect to a separate switch that is running in boundary clock mode. But this is to be avoided if possible. Due to the fact that very few client devices support White Rabbit, only basic PTP is used. Clients use advanced network interfaces and client applications. While it's possible to use basic interfaces and applications, the accuracy of the UTC offset is likely to suffer. In the event of a double failure, clients in a data center could be synced to a node in the opposite data center or to the data center PTP service. Obviously, these PTP nodes could be an excellent NTP source, but care must be taken not to overburden the node in this way. For this reason, it's best to use a PTP node as an ingest node rather than an NTP distribution node. As previously noted, PTP can only have one source or master clock. In the event that it fails, another master clock must be chosen. This failover can be handled in a proprietary manner by the 2 PTP nodes on a site, allowing one to emulate the other or by using virtual addressing. However, it's more usual to allow the clients to select to use the remaining node using the BMC Best Master Clock algorithm. Since this is a client function, the PTP nodes do not take part in this directly. For this reason, any deviation between the two available clocks will become immediately obvious to the clients, and a step or slew adjustment may be necessary. In the event that a client application fails, or it loses all PTP service, it is assumed that an unconstrained internal clock of a server can drift by up to 30 microseconds per second, pushing it well outside the expected UTC offsets extremely quickly. For this reason, it is imperative that the BMC failover is achieved very quickly. If this does not satisfy the business or technical requirements, it may become necessary to upgrade the server clock hardware. This can be done using a PCIe card, using an OCXO-based clock. This reduces the drift to under 1 nanosecond per day. This covers most requirements. Further preservation of the clock can be achieved by using a PPS service. In these cases, the node's clock frequency is held in sync by separate cabling to the time signal and may persist during the failure. This means that the node's drift rate is significantly reduced. White Rabbit can function in this way because it's a layer 1 technology, but is less deterministic. While there are a range of options to support time services, the implementation is most likely to be based on requirements and available budget. The technical architect must drive out the requirements to arrive at the appropriate solution. There are many factors that will make it impossible to reach these optimum UTC offsets, with poor architecture, poor hardware, poor software, and poor configuration being most prevalent. I hope you've enjoyed this run through the options for enterprise time services solutions. Please leave any questions in the comments. I will respond to them as soon as I can.